It is my great pleasure today. I'm David Morrison, by the way, the director of the Carl Sagan Center. I'm getting to know everybody, and I hope you know me. I actually have had not that much interaction previously with our speaker, Richard Quinn. He got an undergraduate degree at Rensselaer, is that right? George Washington, I'm sorry. And then studied in Europe and has been at Ames and SETI for some years. He is a chemist. And he could be considered an astrochemist, but in fact, he's become deeply involved in the development of small payloads and instruments. That's what he's going to talk to us about today. His subject is this, Oreo cookies. However, he likes to pronounce it with an O in front, and I guess at NASA one can't in fact do a product placement. But I think it's easier to remember this subject as being Oreo, which has had a great success, was successfully launched, and we're going to hear about some of the results and some of the technology for future missions. Thank you, Richard.
Since I have a bit of time here, so I'd like to just start off by acknowledging the vast number of people that were involved in the mission. The credit for the OREOS acronym goes to John Rummel. And the origin of the Astrobiology Small-Payload Missions program actually started at NASA Ames during a workshop in summer of 2007, I believe. And this mission is the first technology demonstration for the program. It's an ongoing program. There should be a call coming up in the fall. And I'm going to focus today a lot on the technology that went into developing the mission, and hopefully some people in the audience will view it as a platform that they can use for their own research and their own experiments. The supporting scientists are a group of postdocs over at NASA Ames and Gio Manelli over here who really did the backbreaking labor. And I'll show you some photos later on. You'll see he's smiling. He still smiles. It was really, really difficult mission to put together. It was done very quickly. I believe the original baseline was 18 months. We had some launch delays. But then we had Nathan Bramall, who actually is now at the SETI Institute. He did a lot of work on basically the fabrication of the tools we needed to put the instrument together and the spacecraft together. Katie Bryson, who did a lot of the characterization of the science for some of the films I'll be talking about, some of the samples that we sent up into space. Julie Chittenden. Amanda Cook is doing ground controls currently over at NASA Ames. And Julie also had a lot to do with the chemistry that I'll be talking about today. The science team, I put second because we're less significant. Pascal Ehrenfreund is the project scientist. Probably a lot of you know Pascal. She's been a friend of the SETI Institute for many, many years. Rocco Mancinelli, who I'm sure most of you know. Andy Mattiotta over at NASA Ames, Wayne Nicholson, myself, Tony Rico, and Orlando Santos over at SETI Institute. The operations for the mission are being done just down the street at Santa Clara University. And it's being run by Chris Kitts. And the downlink is actually being done as a student outreach activity. And then the engineering for the whole satellite and everything was done by NASA Ames Small Payload group. And then down here, I have some of the headquarters people in lowercase letters here. Kathy Conley, she's the program scientist. Project manager, Dave Squires. And then we also have the instrument scientist, is Tony Rico, in mission operations. So the objective of the Astrobiology Small Payloads Program is to do very inexpensive, relatively speaking, quickly developed missions that give scientists the opportunity to do their research in space. I think a lot of people might be familiar with the decadal survey that just came out, and by looking at it, you realize it's very, very difficult. It's a very, very long road for NASA scientists to actually fly an instrument or to do something in the space environment. And the objective of this program is to make that easier for us. And so again, as I go through this and I'm describing the technology, really think about it and say, okay, this November, what can I do with this technology? How can I respond to this AO that's coming out? Because really this is a platform technology demonstration that was developed specifically for that purpose. So the OREOS, it's actually a dual payload system. We're doing 2 experiments. The first experiment is to expose biological organisms or spores to the space environment and look at viability or survivability in the radiation environment. The second is to look at organic compounds directly in the space environment and to use in situ detection technology. There have been a number of experiments done on the space station, space shuttle, where experiments are brought up and then the scientists wait around and then they come back and they work in their laboratory to analyze the data. Primary objective here was to do everything in space, to send your samples up, do it in orbit, and get your data back in real time. And we successfully launched on November 19th last fall. This was after a couple of delays. One thing about this I'll touch on, this is a secondary payload, meaning we're piggybacking on a more important mission. So when you're developing these types of experiments, it's really important to keep in mind that you may be delayed. And it becomes an issue for biological experiments where you might have a shelf life. So that has to be incorporated into the design. I believe we were probably we were completely ready to go about 8 months before this. And originally we were supposed to be done even, basically, we were about a year late, I believe. So the objectives is to investigate the effects of a variety of astrobiologically relevant parameters and environments on the chemistry of organics and biological samples in space. So to cut this to the chase, really what we're doing here is, when I talk about environments, to me that means that we're establishing and controlling to a certain extent reaction conditions in space. We're basically sending up test tubes that can do certain things, that hold certain reagents, that are controlled in certain ways. So that's a way to think about the fundamental approach of the experiment. And that's what makes it sort of universal, where it can be applied to a lot of different disciplines. And then what we want to do is we want to look at the survival, the adaptation, and the biological evolution of these samples over a long duration in space environments. So the basic structure of the spacecraft is based on a standard cubesat, 10 centimeter cube. And there are 3 components to this spacecraft. The first is just, well, not just, but it's the bus, it's the control system. Housed in another 10 centimeter cube is the biology experiment. Biology experiment is called Sessler, and I will tell you what that means when I can read the chart that has the acronym spelled out later. But just as sort of an overview, what's being done here is we have 2 different spore types, and they're being sent to space in the dry state, and then at 3 time steps, a growth medium is introduced to them, and we're looking at viability, whether or not they germinate, they spore, they grow. And we're looking at optical density in real time to measure growth. The second experiment is called the SIVO experiment. And I'm actually probably going to be leaning a little more towards the description of this instrument, this experiment, because I was more intimately involved with this one than the growth experiment. The growth experiment, I would say that Rocco Mancinelli and Wayne Nicholson were the leads on that, while myself and Andy Mattiota were the leads on this one in terms of the science. And what we're doing in this one is we are taking a number of different organic molecules. We're putting them in reaction cell supported environments. These are the test tubes. So we're setting some reaction conditions for organic molecules. And then in this case, we're using UV visible spectroscopy in real time to measure changes in these chemical cells. And then the spacecraft itself is, of course, enclosed, and there's solar panels to provide power to the instruments. Here's a schematic of the spacecraft, and over here we have a beacon radio. Here there is the micro-hard radio for basically for the data. Attitude control, so this is what keeps it positioned in space. And then here, interestingly, this is it's interesting to me because I was not familiar with it. This is the first satellite mission I've worked on. I've worked on some planetary missions, but this here is basically a little sail pops out, and that creates a little bit drag because there's I guess international law that the satellite has to deorbit within 25 years. So basically, it pulls some drag to make sure that that thing comes crashing back within 25 years. And here's some pictures of the actual hardware. This here is the SIVO experiment, the organic experiment, and that's housed right over here. Here's the biology payload experiment, and then the control bus. So as I said, we lifted off finally in November. The development time, about 18 months for the entire mission, not counting some delays. And I guess a picture of the bear, all the science team, very excitedly, we were talking about, we're going to go to Alaska, we're going to watch this launch, it's going to be so great. This is about beginning of the mission, but then as it got pushed off to the cold, dark November days, we all stayed at home and watched on a teleprompter over at the visitor center at NASA Ames. So some the details of the spacecraft parameters. So we're spinning around the Earth at about 90 minutes, complete. And then, as I mentioned, the positioning is passive, and the spacecraft itself is rotating. It's rotating this way and that way, coning rotation, and I'll talk about it a little later. In terms of our data collection, all of this had to be modeled in terms of what types of rotation rates we had. And initially, rotation was quicker than we expected, and it took a little bit of time for us to work out the parameters in real time, send some commands up to the spacecraft to control our data collection sequences. We get basically on average 4 passes a day to collect data. This is, as I mentioned, over at Santa Clara University, but only 2 of those contacts are good. The average contact time is 2 minutes, and we're going to get a total of 730 minutes contact. So again, if you're thinking about designing an experiment, you really have to think very carefully about what your data requirements are going to be and keep them to the absolute minimum. We have a 6-month mission, and we've got about 10 hours of downlink time. So it's very difficult to downlink the data. It's very time consuming. We're getting a very small number of data packets per each pass because they're only 2 minutes. And here's just a picture of the viewing angle in terms of the latitude and the position of the spacecraft relative to Santa Clara University and the ground control station. So what are the space conditions that we have? Well, there are 2 types of space conditions. There are the space conditions that are provided to us by being in Earth orbit, and then there are conditions that we create in space. So to start with what the actual space conditions are, what the experiments themselves are subjected to in the radiation environment. For the biology experiment, of course, we're at microgravity, which is a critical parameter that we want to investigate. And then also, we're subjecting the spores to ionizing radiation environment. If you remember the picture actually looked like had a gold plate. Well, the spores are not seeing any solar UV or visible light. They're in a black box, but they are getting irradiated with ionizing radiation. The organics, on the other hand, we are exposing them intentionally and directly to solar radiation because we want to see what the effect of solar radiation is on organics in the interstellar medium, or say on Mars or other planetary bodies on the moon. We're also, of course, mentioned here, it's also microgravity, but for the biology or for the organic experiments, that's less of a parameter of interest, although it may affect your experimental design. To keep things cheap and quick to the extent possible, everything was commercial and off the shelf in terms of our sensors. So what do we have housed inside the spacecraft? Well, there are pressure sensors, and that's to monitor the pressure inside the bioblock for the Sessler experiment, for the biology experiment. Temperature sensors on both payloads, and then relative humidity sensor again inside the bioblock for the Sessler experiment, the biology experiment. Both experiments, SIVO and Sessler, have radiation sensors, so we can get the total ionizing radiation dose. Light intensity sensors are needed for this organics experiment, so we know when we can collect a sample. We need to know where the sun is positioned relative to our instrument, so we know when we can proceed with data collection. And so we have two types of light intensity sensors. Some details on the sensors themselves. They're integrating their dosimetric, so we're getting a total accumulated dose over time. The heritage for all of these sensors date back to 1978, very long time, so there's extensive heritage for these sensors. And then they don't need to be powered for dose accumulation, only to actually read. And then the other thing is, I'll talk about a little, it's not so straightforward in translating the accumulated doses in these sensors to what the biology specimens or the organic specimens are seeing. I'll talk about that a little later. So how much radiation dose are we seeing here? We've got RADs. We've got about, over the course of the duration, you can see here our two experiments received different ionizing radiation doses, and that's due to shielding, basically how these things were built and put together. For the SIVO experiment, we get a higher radiation dose than for the Sessler. SIVO, our samples are basically protected only by a magnesium fluoride window, while the biology experiment, due to technology constraints where we had to pressurize and heat a bioblock, in that case it's a much thicker level of shielding due to the structure itself. So we actually get a little bit lower dose for the biology experiment, which is somewhat unfortunate because that's where we might want to see a higher dose rate. But if we do a comparison between what we're getting here if we compare this to what you see on the space station, we're actually getting about an order of magnitude higher level of ionizing radiation dose. And in fact, the initial data coming back, which hasn't been fully reduced yet, indicates that our dose rates are much higher than we initially had modeled. And then also another note about sort of the contrast to the International Space Station. Of course, one of the difficulties for scientists is actually getting a payload to the International Space Station. And really, a major goal of this was to do a comparison in terms of total costs. Can we do two payloads simultaneously and do it at a lower cost compared to trying to do a space station experiment? And it turns out, of course, it is very, very favorable in terms of the economics of doing science that way. But also, it's a better environment. As you can see here, we get better ionizing radiation dosages. And also, you get better field of view to the sky, to the sun for your exposures and to do your science. I don't remember the exact numbers, but Pascal Ehrenfreund has done a number of experiments on the space station where they send up trays of organics and they bring them up, and they're basically at the mercy of the larger mission as to how their experiment. I see some people nodding. They've probably gone through the pain. But I've got a picture of an astronaut, maybe at the end, I think, a backup, holding Pascal's experiment between his knees, touching it with his hands, and then mounting it upside down. And then wanting to know where the on button was. So you have much better control about how you deploy your instrument, how you do your science when you're doing a small payload mission. So Sessler, I promised you I would tell you what the acronym stood for. It's Space Environment Survivability of Live Organisms. So the objective here is to test how microorganisms survive and adapt to environmental stresses of space. And 2 spore types are being flown. And again, the next few slides, I'm kind of just going to touch on this because really Rocco Mancinelli and Wayne Nicholson are the scientists behind these experiments. But I'm presenting it here again so that people who do biology experiments, and you can tell your colleagues that this hardware is there, it's at Ames, and it was built to be on the shelf and available for scientists who go through proposal process for the small payload missions. So what's happening in this experiment is nutrient is added to the dry spores at 3 time points. 2 have been successfully executed already, and we're looking for the 3rd to be completed in June. And again, I'll talk about a little bit the details here, where just the platform for this is, here's the well that houses the spore. And you can see what they're using here is a fluidics card, a multi-layered fluidics card, where they are, at a given time step, they can pump the growth medium in. And then what they're doing, well, let's see, we have some heater layers here. So of course, we're in space. We got to keep this warm, keep everything fluid. But then what they have here is a series of 3 LEDs that are pointed downward through your culture media and looking at a detector, so you can look at changes in optical density at time at 3 different, 3 different colors, 3 different LEDs, and you can determine which of your spores remain viable as a function of time and radiation exposure. There are 3 independent bioblocks because there are 3 time steps, and you can see here there are multiple wells within the fluidics card that house the spores and then have the medium pumped down through it. And here's a CAD drawing of the unit itself. And again, keep in mind in terms of the size here, there are 3 of these housed in a 10 centimeter cube. So it's a very small experiment. And I think you can see here, you can see the wells and the profile here. And then in terms of radiation monitoring, there's 2. There's a RadFET, and the RadFETs are both on the top and the bottom. And the bottom panel of the Sessler actually was thin so that more radiation exposure could happen over the course of the experiment. So as I mentioned earlier, in this case, here's basically the panel for the biology experiment. So it's completely shielded from UV, from solar radiation. We're looking at the ionizing radiation. So then, how do you actually determine what the estimated or the real dose rates are? And I'm not going to read this, and you're not going to read this. There are some engineers here who might be able to explain this to all of us, but it's actually quite complicated. You have to do comparison to other missions, to other payloads, other spacecraft, and then you have to model what your daily radiation dosage for the biology experiment. Okay, so next on to the space environment viability of organics experiment, the SEVO experiment. And this is the experiment that I was more intimately involved in. And what we're doing here is we're taking 4 classes of organic molecules and exposing them to the space environment. So OREOS was a technology demonstration mission. So in terms of the science, we try to go very, very broad to show to the community some of the capabilities and some of the different types of science that you could do with the instruments. And that's where it comes into this. Specimens are maintained into 4 different self-contained microenvironments or reaction cells. For each of the organic molecules that we chose, there was a science justification. I think a lot of people are very familiar. PAHs in terms of interstellar media. Their most abundant stable material delivered to Earth is aromatic molecules. We find them in meteorites. It's a major mechanism of transport of organics in space. So even though we had science rationale behind all of organics, we also had some very real technology constraints. We're using UV vis spectroscopy to measure these, so we had to have organic compounds, one, that we could deposit in a manner that allows us to measure them spectroscopically. Then they also had to have a significant absorbance in our measurement range. So we did have constraints, and we narrowed things down to where we would look at a large PAH, a quinone, a porphyrin, and then an amino acid. The porphyrin being iron tetraphenylporphyrin, other hemoglobin is a porphyrin. Very interesting biological compounds in terms of charge transfer chemistry. And then tryptophan, amino acids, so very important in terms of basic fundamental origins of life chemistry. And again, we're measuring the radiation dosage in the SIVO experiment. In this case, we have a rat fit over here. And then I think I'll show some pictures later on about how we're also measuring the UV vis light that's impinging on our films. So the shielding is using a mag fluoride windows, so it's much less severe than the metal plate that you saw for Sessler. So in terms of the science, well, what are we doing? Again, we went broad. And we also went broad because it was technology demonstration. Also, we have our science team or working group. We actually come from different disciplines. Pascal is interested in interstellar media. I'm more of a Mars type of person. Andy Mattiota had some Mars science going on. So we all kind of had to do some trades in terms of what the science was going to be. But it also enabled us to show how we could do different science for the mission. So our environments, what are we looking at? Well, we're looking at a vacuum system. Now we call it a vacuum, but in fact, in terms of the technology, our cells, our organic samples are held in an inert argon atmosphere. So something that will not interact with the solar radiation. Mineral surfaces, that's relevant to moon, asteroids, planets, protoplanetary disks. We're looking at substrate effects. In other words, catalysts on the reaction chemistry. So we wanted to make a system where we could also do catalytic reactions. We wanted to look at planetary atmospheres. We want to show people, well, you actually can carry gas into space. It just doesn't have to be a fluid, or it has to be a solid. You can carry gases, and you can do experiments that are relative to planetary atmospheres. And then planetary surfaces. We wanted to demonstrate that you could do humidity control inside these little test tubes, these little reaction cells. And I'll talk about that a little bit later. But of course, the impact of water activity on chemical reactions is intimately tied to the origins of life and habitability. So it's a key question in terms of astrobiology. So how do we make our samples? The samples in this case, and again, this is the technology demonstration. As I go through it and you look at the pieces, really think in your head, well, how can this be done differently? How can this be done with different science? But what we did is we sublimed our films onto optical windows. And here's a picture of the equipment put together in my lab to do this experiment. And here we have a high vac chamber to allow us to do our depositions. Here's a masking system. And you see these little holes on here. Each of those hold one of our windows. So we do our depositions, we prepare our samples in large lots. And we do that so one, we have flight spares, two, we have ground controls that we can go back and we can do experiments during and after the mission. If we did the film depositions in multiple processes, then we would end up having variations in our films, which would impact negatively on our ability to interpret the experiment. So we used mag fluoride substrates for vacuum environments. We wanted to make sure we could get down in deep UV, Lyman alpha, so mag fluoride were used for those experiments. We used mag fluoride with a sputtered layer of SiO2, and that's our catalytic surface. Very, very thin 5 nanometer coating for the mineral surfaces. But you can think of, or I can think of tons of experiments where you could put TiO2. You could put all sorts of materials down on these windows to look at the interactions in terms of catalysis and different chemistry types. We also put down alumina or sapphire done as, again, a sputtered film. And in this case, what we wanted to do is we wanted to cut off the UV light so we could mimic a Mars environment. And so sapphire do that for us. And also it allows us to contain water vapor within our cells. Mag fluoride is actually going to degrade or react with water vapor. So it's a protective coating, but it's also a light filter for our experiment. So the next challenge after doing our depositions is we have to hermetically seal these reaction cells. The requirement was, I'm not sure if it's on this slide or it's on a later slide. Oh no, here it is. We had to have less than 10 to the minus 6 times 10 to the minus 10 millibar liter seconds. What that means is we have very, very small volumes. This volume here is probably on the order of maybe 50 microliters. And our requirement was that we lose less than 20% of the headspace gases over the duration of the mission. To do this, what we used was a cold compression welding. And typically, if you look at sealing of packages, they will use a seam sealer type of thing in electronics where you have a metal and then you heat it to its eutectic temperature and you bond pieces together. What we did here was a metal gasket, but it was an indium gasket, so we could just simply compress these and do these very, very cheaply and inexpensively in our lab. And they do hold well enough to meet our requirements. And then within this little space here, we have our argon, the controlled humidity, and trace CO2 and trace oxygen. So this actually mimics Mars atmospheric conditions. The controlled humidity, the way we did that, I'm not sure if there's a slide that shows that. The controlled humidity, what we did is we immobilized a hydrated salt around the perimeter of the walls. So basically there was an insert cylinder, and by using, in this case we used a nitrate dihydrate, we're able to buffer the partial pressure inside that cell at about 3 to 5% relative humidity over the duration of the entire mission. And the 3 to 5% has to do with the temperature variations that the spacecraft goes through over the course of a day. So once we've sealed up all our cells with the different gases, they're placed into our sample carousel. Here's a schematic of it, where we're carrying a total of, I believe, 24 samples. Some of them are references, some of them controls. And this outer surface is, the sun is pointing down on it to initiate the chemical reactions. So here's a picture of the spectrometer. Again, everything is very small here. The carousel, it's about yay big. It's less than 10 centimeters in diameter. The spectrometer is very small, very compact. what we're doing here is on our carousel where we have our samples housed, the sunlight is coming down on them. We use a baffle diffusers to basically spread out the light, make sure we get uniform light across the samples. And then we have a fiber optic system that feeds into the UV spectrometer. There are 2 fibers. To increase the packing density on the sample wheel, they're run in an inner ring and an outer ring. And because of that, we're required to have 2 fibers to take our measurements. So the sunlight is the source for the spectroscopy. In the laboratory, if you're using a spectrometer, you always it has its own light source. In this case, we're using the sun both for the chemistry and also to take our measurements. So you can see here the sun shines through the samples where we measure the absorbance of the films and changes in absorbance with time, and then it's picked up by the UV spectrometer. And then the stepper motor simply moves the sample's position through the light path for the optical fibers. So, and this is a schematic of a top view of it. So here's the sunlight intensity sensors. So again, in terms of collecting our spectra, if we're using the sun as our light source, we can only collect data when we're pointing towards the sun. And that's a problem for us with a rotating spacecraft. So it's equipped with sun angle intensity sensors and then a programmable set points in terms when the spectrometer turns on, turns off to collect data. Here's the complete schematic of it, and here you can see over here where on the sidewall is the hydrated salt carrier along with the indium gasketed seals. Down underneath our sample cells we have culminators, so we actually collect the light down into the fiber systems and down into the spectrometer. And here's how the solar diffusers are positioned over the samples. So the solar diffusers are only over the samples when we're actually taking a measurement. During all other times, the samples are exposed to full sunlight during, as they rotate, as it rotates along its axis. So the peak timing, so how do we actually collect our data here? And I have to read this one from the screen. But this is what I was mentioning earlier, where initially we had an issue with our data sets where the spacecraft was rotating much more quickly than we expected. So our timing was a little off on when we were going in there to collect the data. And you can see here that basically what we have is a threshold intensity sensor that says that when you get within a certain acceptance angle, to turn the spectrometer on, collect the data, and then turn off. And all that is key to the rotation rate. So initially there was quite a bit of tweaking that needed to be done to get those parameters right. But of course that doesn't affect the experiment and the data itself, because this is simply a data collection issue and it doesn't affect the exposure of the samples to the space environment. So the specifications for the hardware, we're exposing all the way down Lyman alpha range up to IR range for our samples. We're exposing for 6 months, but only 35% of that time is actually exposed to the sun because of the rotation rate. We have typically an integration time of 100 milliseconds. I'm not sure what it is now. And then we're onboard spectral averaging, 16 spectra to be returned down as part of the data packets. Our temperature range is minus 30 to 30 plus. So again, that's something that you have to consider carefully when you're designing the experiment. You can't be working with materials that are volatile to the extent where if you go, 30 degrees or even above, since usually you have to put in a margin of about 15 degrees there, and also in terms of the lower temperature limits. And then I've mentioned all this, and then again, going back to the people, some point people out. Some of you know Nathan. There's a picture of Geo right over there, sitting in the audience. It's incredibly labor-intensive exercise in a very short period of time. Here's Julie Chittenden doing the depositions. Can't really see, but she's plexiglass glove box there. All the sealing, everything was done in inert atmospheres. And then here's some more testing. Andy Mattiota over here. So there's a huge amount of work put into this. So what's the current mission status? Well, as I mentioned, successfully launched after a couple of delays. Total weight of the spacecraft is only 5.5 kilograms. The baseline, so right now the mission we described as nominal. All the instruments are healthy, the bus is healthy. Initially we had a rotation rate of 7 RPM, now we're down to the expected 1.6. It's always fun. I was planning one funeral already. I think I was like the least optimistic when we lost communication with the spacecraft. After we had gotten our data back and we had gotten most of the, we had hit our minimal mission success criteria, but we lost communication. But it came back, well, it didn't come back to light, but things turned back on. An interesting thing I didn't mention, and I think it's right here, the beacon packets. We have 25,000 or let's say 35,000 packets submitted by amateurs in 17 countries. This is something, I guess for the SETI Institute, people are very familiar with community involvement and community excitement about these types of science missions. But the first notification that the spacecraft was alive, that had successfully deployed alive, I think came from somebody in Switzerland or something like that. So it wasn't the engineers themselves. There are a lot of very interested people in the public who are helping us out with the mission. In terms of data pages for ourselves, for the science, 700 data pages. We've gotten the data back from the first 2 biology experiments, and we've gotten far more spectra back than I ever expected to see. It turns out that Santa Clara University, they're doing a great job pulling everything down, so we'll be getting a complete data set. Again, the biomodule experiment, 2 have been done. The final one is going to be in June. And the time 0 showed germination and growth of all the spores. So we know that our time 0 data point is good. For the SIBO experiment, 19 sets of 24 samples of the spectra have been recorded. 75% spectra have been downlinked. It's actually more than that now. This slide, I think, was actually put together for LPSC a month ago, so it's changed. We've gotten a lot more data back here. And then we've been going through a continual sort of tweaking in the parameters to optimize the spectra, but they're actually looking pretty great now. This is very hard to see, but I think they upload these slides. But the web link down here, you can actually look at the Mission Control Center in real time, and you can watch the tracking of the satellite. And they used to have live video feed of the people over there actually collecting the data. So it's actually pretty interesting to watch and get a current mission status. So just a couple of summary slides here. So what's new here? Again, prior to the OREOS mission, the type of experiments that people have been doing have been limited to basically what could be considered passive. You had to build your experiment, and then you had to wait. You had to get it on the shuttle, you had to get it to the space station, you had to then wait, have it come back and do your analysis. So what's different here is that we're doing the spectroscopy in real time. We're getting our data back. We're getting a lot more data points that allow us to understand mechanisms, what's really happening with the science, rather than simply a before and after. The sample cells is a new technology that's now available for people to use. The glove box and everything, I mean, it looked complicated, but it's actually not. It is labor intensive. But what we were able to do was to hermetically seal a number of different environments. We used a Mars atmosphere, but you could imagine using any sort of combination of gases you might want in a cell to do the science that you're interested in. We did SiO2 as a catalyst, but there are hundreds of thousands of other materials that could be put in these types of cells to look at chemistry in space. And then the humidity control, we peg the humidity at 2 to 3%, but by changing your water source in terms of what your salt is or how you hold that water on the sidewall, that'll change the humidity. So you can imagine having an experiment where you look at different things as a function of humidity, where you have very low humidity up to very high humidity as things are exposed in space. So there's a lot that can be done with the technology. The Sessler, for the first time, basically we had all in 1 centimeter cube, this complete, really robust fluidic card biology experiment with thermal control, optical detection, and then the ability to monitor the science over a 6-month period, much higher dose rates than you would ever get on the space station. So future possibilities, I've been talking a lot about this, and this is a very old slide. It's done before the decadal survey. So a lot of these things actually may be off of NASA's map. But really what this is an opportunity for scientists at the SETI Institute to get their experiments up into space, to really move out of the lab, to move out of doing the theory. And it is really meant to be available to scientists. It's going to be competed this fall. There should be a call coming out during the salmon, as a Rose's salmon call. There was a call done, I think, about a year ago. And some of you may have seen it and may have decided not to apply because it was extremely technology dense. There was a proposal information package of several hundred pages, and the PI had to write the technologies side to say, how were you going to do this? How were you going to do the mission? Where were you going to launch from? What were all, which is really not what we do as scientists. So the AO has been rewritten. I haven't seen it, but what I hear, it's going to be very specific for research so that scientists can propose experiments using existing hardware and not have to go through the burden of explaining how you're actually going to get it, up into space and launched. And that's all I had to say about the mission. Thank you. If any has any questions?
I have one. Can you give a little more perspective on the comparisons between these platforms and the International Space Station? In terms of radiation, I mean, I don't see how you calibrate what's what. On the space station, it must be very different on the outside from the inside in a rack. And here it depends on the exact orbit you go into. Is this a controllable situation? Can you really compare data from both?
That's a good question. And one thing I didn't touch on, one of the justifications of the mission itself was as a comparison to what are people getting. A lot of people do exposure experiments in the laboratory where they try to simulate conditions of Mars, simulate different things. The same thing where a number of experiments have been sent up to the space station, and the parameters are very different. And cross-comparison between what's been done in the laboratory and what's been done on the space station is very difficult. and they don't seem to correlate. In terms of OREOS, the benefit here is we get more. We get more radiation exposure. We get more ionizing radiation. We can run these experiments much longer. As Dave mentioned, the positioning where you get on this space station influences a lot, what your experiment is, what your dose rate is, how long it'll be up there, and how it's deployed. So it's the mission itself is to overcome some of those challenges and to make it more accessible and to be able to do longer, more robust. So in terms of the amount of exposure, it's in terms of the ionizing radiation, it's better than an order of magnitude per unit time. And the experiments, some of the exposure experiments have been, I think, up to 18 months or so. But this is a 6-month experiment, but we're getting an order of magnitude better in terms of our ionizing radiation dose. We're spending much more time in the sun because on the space station, most of the payloads are inside. They're not docked on the outside.
Question? Yes.
Hi, I'm Bart Smith. I'm just an interested amateur. What principal results do you expect to get from this experiment? And if they confirm what you expect, what's the significance of that?
Sure. And I apologize a little bit. I think when Adrian asked me to give this talk, he thought I would be talking about mission results. As a science team, we're not talking about our results until publication. We're holding back our results that have come in. But in terms of the significance, I think that the results are going to touch on a large number of different disciplines. I think one that comes immediately to mind is the planetary protection issue in terms of the spores that are being flown and what is their viability in terms of planetary protection, in terms of moving organisms through space over a period of time. In terms of the science for the SIVO experiment, myself, in terms of the Mars experiment, I've been extremely interested in the difficulty people have been having detecting organic compounds on Mars. It's been attempted a number of times. There's a new result that maybe they were missed because perchlorates are decomposing things. But even if that's true, the inventory of organics in the near surface are very, very low. And so this experiment directly addresses the mechanisms that's basically degrading biosignatures and degrading organics in these environments.
I'm Jeff Scargill. I have just a couple of quick practical questions about the ground station at Santa Clara University. What's the deal there? Why not at Ames? And is that where all future missions will have their ground station? And the second part is, well, go ahead with that.
I've asked the same question, and I think that one of the great missions of NASA is public outreach and to excite the public. And for a mission like this, which is very, very low budget, very resource constrained, it was a good idea. It is a good idea to utilize those facilities. The downlinking is being done as part of an engineering curriculum at the university to train students to be scientists to work at NASA. So that's the logic behind the ground station. Plus, the students are also willing to wake up at 3 in the morning one night, 4 in the morning the next night, 5 in the morning the night after that, and do it for 6 months to collect 2 minutes of data. Basically, holding a coat hanger outside their lab window. Not quite at 3 meters, but it's difficult.
And the other thing is, from the fact that you used a lot of off-the-shelf parts and so on, I gather there aren't as many restrictions on space qualification and so on as there are on bigger missions.
Well, this is, I'm not, at the top of my head, I'm not overly familiar with the categories, but this is a Class D mission, or the lowest level in terms of technology demonstration. In terms of off the shelf, I think I mentioned, to the extent almost all of them have had flight heritage. So they're off the shelf, but it's not necessarily the first time that things have flown into space. But we looked at it very carefully in terms of detectors for the spectrometer and things like that, and we picked the best that we could within our resources, and everything has worked out great. Okay.
Thanks, Jeff.
Hi, my name is Adrian Constantinant, and this is more on the engineering side, which is on the experiment that had the disk, and that would had the stepper motor that would rotate, and it had the sunlight sensors. How was the engineer so that it would determine when the disk would actually turn to expose a new sample to the open environment?
Well, if I understand your question, I mean, I believe that there are some parameters that are controllable from the ground, and that's the duration of how long we're sampling for a particular cell. So when that's done, then everything is triggered to move one step to the next sample, and then the process is simply repeated.
Okay, last question.
I'm Dan Lubins from Scripps Oceanography. A simple but often loaded question. How much did this mission cost?
I don't know. I can tell you how much uncompensated time I put into it. But I believe that and I honestly don't know, but I believe the original budget was $2 million, and that's about what it cost. So $2 million, which is incredibly cheap.
It's a bargain.
It's a
Let's
bargain.
call it inexpensive, not cheap.
Inexpensive.
Yes. We can't even give you a T-shirt, but we do have a SETI mug to show our
Thank you.
appreciation, and it's been great to have you here. Let's
Thank
all
you.
thank our speaker again.